Good morning, class. So today is December the 2nd, and so this is the video for December 3rd, and it's the quiz 3 review. So material sense quiz. Oops. Quiz 2. And so today I'm going to walk through everything we've done since quiz 2 in preparation for quiz 3. And so I'll try to do this in an organized fashion so that the board stays up with everything you need to know. So we left off sort of in the middle of heat engines, and I'm gonna put back up the PV diagram for the Carnot cycle. And where this is T hot, this is T cold, and in these two parts, T is proportional to 1 over V to the N, where N equals 0.4 for air from thermodynamics. So for the quiz, of course, in quiz 2, we sort of we're getting into this part, and for quiz 2, you had to know that the area inside here is the net work per cycle. Of course, you knew that the work was the integral of P dV, and for quiz 3, you will have to understand how, for example, to draw this diagram. I mean, the point that you have to know the ideal gas law, that P is equal to, and we'll continue to use this beta. Where that beta, as you learned from the homework, contains the Rydberg constant and the number of moles. But since the number of moles is a constant, it's a constant for these problems. But the point is that the pressure goes as temperature over volume. So if the temperature is constant, it goes as 1 over volume. If the temperature is falling, it goes as 1 over volume to the n plus 1, and so faster than 1 over volume. So you have to understand what's written here. And this is, for the Carnot cycle. And so, you have to understand how to do things like note that that's T hot there and T cold there, which I won't mess up the diagram too much. But, and also that, to understand that the Qn is equal to, let me see if I can draw this a little bit differently. So for these two parts of the cycle, right, T is proportional to 1 over V to the N. And the Q input is equal to the energy of 1 to 2. We went through that. And the Q out, which is your loss, is equal to the energy from 3 to 4, or the absolute value there. So this is a thermodynamic diagram, and you're putting in heat from the hot water. That's your input, and that's equal to the energy in that cycle. Why is that true? It's because the temperature is not changing. And on this part of the cycle, you're losing heat, dumping it into the cold water. And what you've learned is that that loss, thermodynamic loss, is inherent. And it results in an efficiency thermodynamic, which is equal to T hot minus T cold over T hot for the Carnot. Now for a real engine, so that's for Carnot, and this is for a real engine, a car engine. All right, whatever it is, and we learned the Otto cycle. All right, and I'm just going to sort of draw, kind of an arbitrary cycle here. All right, it's the same thing. In this, in the real car engine, Q in goes there, and Q out goes there. All right, and the point is that a real engine also has inherent thermodynamic loss. And in a car, that's out the tailpipe. Okay? And the point is that for whether it's this Carnot engine or a real engine, in order to have an open cycle, all right, there has to be a part of the cycle where you're dumping heat. And in the Carnot, sort of made-up engine, that heat is being dumped out in this cycle going into the cold water. In a real engine, for a car engine, it's dumped at some point in the cycle, all right, and that's going out the tailpipe, that thermodynamic loss. All right, and furthermore, for a real engine, there's other losses, okay? There's thermal, there's friction, there's combustion. All right, and we learned that the product of these things is somewhere between 15% for that lawnmower engine done back in the homework, earlier homework, to perhaps as high as 30% for a very efficient car. All right, so those are the things about engines that I want you to know. And then we got into essentially electric power. And we sort of started at the beginning there about charge and current and things like that. But you learned that there's capacitors where Q is equal to CV. And if you take the time derivative of both sides, that means that I for a capacitor is C dV dt. This is a definition. Capacitance is charge over voltage. And so basically, I just presented to you that for inductors, there's going to be a corresponding element where V is equal to L dI dt. And of course, you know that resistors, V is equal to IR. Okay, so basically we sort of started at the beginning of physics, and we learned a few things so that we know that there's these elements, capacitors, inductors, and resistors. We learned from our basic physics, from Gauss's law, and how to calculate what C is. We learned from Ampere's law how to calculate what L is, and that's all useful things to know. But the points besides RLC that I want to get across are, okay, AC power, one, so to speak, and there's all kinds of interesting popular movies and stuff about that, Tesla versus Edison, which is kind of interesting. And it won because of the transformer. because you want to have high voltage in your transmission going down to, and I'll draw it out so that I kind of save space here. Let me draw this one with more coils. All right. Okay, and you learned that in order to have low losses in your transmission, you want as high a voltage as possible because then you have as low a current as possible. But we can't have 600,000 volts coming out of our outlets in our houses. And so you learn that there's this device that Tesla invented, the transformer, which is a pair of coils where V gen over V load is equal to, if this is N1 and this is N2, is equal to N1 over N2. But that device has to be, that will only operate for AC, and so we basically learned that that's why we have AC power. All right, all right, and so going forward, you basically learned that that AC power is determined by IRMS, VRMS, where like VRMS and IRMS are V peak for the AC signal over root 2. And that just comes from doing your sine and your cosine. And you learn that if that's for in phase, and you learn that if, for example, if out of phase, then it's W equals IRMS, VRMS, cosine phi, where that's for if V is, for example, is sine omega t, and I is, I'll write out Vt, Ip, sine omega t plus phi. Okay, and then this is called the power factor. Sometimes PF. And am I still in focus? Pretty good. All right. Okay, so let's pause for a moment. Just checking my focus here. You can read everything. You know, sorry, it's a little bit off. But I'm trying to pack everything in there so I don't do any erasing. Maybe when I'm done, I'll try and make the focus a little better. So, you know, so far, you know, from quiz 2, heat engines, we learned the Carnot engine. We learned how to calculate a thermodynamic cycle. We learned that the efficiency of a Carnot is T hot minus T cold over T hot. We learned that real engines have some kind of PV diagram where for both the area in the curve is our net work per cycle, and that both have some sort of input heat and output heat that's inherent, and that's our thermodynamic loss. You know, in the Carnot engine, that inherent loss goes into the cold water in that part of the cycle. In a real car, that inherent thermodynamic loss goes out the tailpipe. And a real engine has additional losses, friction, combustion, and there's an overall efficiency. Then electric power, you know, CLR, or RLC backwards. You learned about them. You learned that there's this device called a transformer. It's a pair of coils that allow you to, for AC, step voltages down. And so that's what won for our distribution system, because then we could have high voltage in our distribution and low wire losses, while we had low voltages on the load. And so we learned about RMS, where the RMS is the peak divided by root 2, and so from sinusoids, W is for AC. IRMS, VRMS. If they're out of phase, it's IRMS, VRMS, cosine phi, where cosine phi is the power factor. Phi there is, for example, the out of phase, the phase difference between current and voltage. So like if V is Vp sine omega t and I is Ip sine omega t plus phi, that's the phi we're talking about there. Okay, so let me go to the next board here and see if I can keep myself in focus. I think I'm doing that. Okay, and so then we learned about electric generators. Which is basically a magnet moving past a coil, or a coil moving, it's all relative, right? So either the magnet moves past the coil or the coil moves past the magnet. You learned the first simple generator, a coil moving where B is into the board here, and you learned that the voltage developed is equal to d phi dt, where phi is the flux, which is B times A. All right, and very important, and I'm not putting the minus sign there on purpose because I don't want you to get hung up on minus signs and things like that. And I could put the absolute value of the voltage, but I'm just going to write it this way. The voltage developed is the change of phi with respect to time. And you basically learned that phi is B times A, where A is the intersected area. And either one can change. I mean, either B can be changing or A can be changing. And so for this generator, if this is moving with the velocity V, okay, it works out that the voltage is B, which is a constant, times d dt, if this is h, of hx, where x is this distance. Too many x's, sorry. I should draw B coming out of the page so they're dots, you know, like the arrow thing. And so h is a constant, and so dx dt is B, so that's B h V. And you learn that if there's a resistor here, okay, if I put a resistor there, that doesn't change V. V is just V, but that will result in an I, which results in a force opposing my pole, and that force is IHB. Okay, and so you learned about electrical generators. You learned how to calculate the voltage developed and the force, and so W electric. Well, here, let me do, so W mechanical, remember that's force times distance, so power is force times velocity, so that's IHBV, and W electrical is IB, so IBHV, and they're equal. And so you learned that an electrical generator, theoretically, can be 100% efficient. Whereas your heat engine has an inherent thermodynamic loss. Okay, and we also did a rotating generator, and the point there is that you have, now while I didn't draw the sign there, okay, you have to realize that if I'm pulling it one way, remember the homework problem, okay, and phi is going down because the area is going down, okay, that's one sign, whatever it works out to be. If I push it the other way, right, that'll change the sign of the voltage. Okay, so you have to, be cognizant that okay, while I don't want you to get hung up on figuring out which sign it is, to realize that, well, it can change sign. Okay, for the rotating generator, we figured out that, of course, as it's rotating, this sign is going, the sign of the voltage is going through a sinusoidal change, and that gives you an AC voltage. All right, and then finally that brings us to the last lecture, and so, I'm just repeating it. So this is energy efficiency. And I'll just repeat, the five, things we learned in the last lecture. Miles per gallon is proportional to 1 over V squared. We learned that the power of a motor is proportional to V cubed. This is speed drives. And that's a motor for a pump or a fan, because V cubed is the power and the flow of anything. And this is, versus V for on-off control. So depending upon what your duty cycle is, you get that savings, and I won't write that down again. The third, oh, I skipped one. Did I skip one? Speed drive. No, I think I did it right. Oh, yeah. The third one was the concept of COP, which is that if I have W electrical, okay, and inside here is, some vapor compression, refrigeration, I'll write machine. Okay, that if you have W, I'll write this bigger. So the vapor compression refrigeration cycle, I didn't try to teach you that. Okay, it is very interesting for some of the engineering students in the audience. I mean, you have been presented it, but this can be an air conditioner or a refrigerator, anything that pumps heat. And the point is that electrical in, and if this is the W heat pumped by the thing, so in the case of your room air conditioner, that would be the heat pumped from inside to outside. In the case of a refrigerator, but that would be the heat pumped out of the box, so to speak. All right, that there's things, this COP, which is W heat over W electric. Now that's if they're in the same units, which is greater than 1, which is a very interesting, concept by itself without understanding what's in this box, that you can pump more heat with less electricity. Running in a room, but 4, we learned about R value, which is BTU per hour is equal to the square footage times delta T in Fahrenheit divided by R. And 5, we learned about heat loss due to ventilation. And you learned that, I'll just write it up, the heat content, I'll write it this way, 2 heat, air, you need 0.018 BTU per cubic foot per delta F, per delta T and F. That's it. I think I was going to mention something here. Okay, in all of this, okay, units. Okay, I mean, you don't have to memorize this, but 1 BTU is 1,055 joules. Okay, you may need to make unit conversion in anything in this class. 1 kilowatt hour is 1,000 joules per second, that's a kilowatt, times 3,600 seconds, that's an hour. So it's 3.6 million joules. Okay, so in any of this stuff, you may need to do unit conversion. So that's throughout the class. All right, so I'm going to slip around here and make sure I'm still in focus. And it looks like I am. Very good. Okay, and so you can see the board there. And sorry it's a little messy in places, but if you look at that board, that tells you everything you need to know for the quiz. Okay, so that's it for today, and I'll talk to you and we'll go over this again in group meet tomorrow.